All right, combining functions. We have been able to add, subtract, multiply, and divide functions, and we're going to just let f of x and g of x be functions with intersecting domains. So these are functions with intersecting domains. All that means is that the domain of one can be used in the domain of the other. So I can basically take these two functions and add them together. I can also write it as f plus g of x. This is function notation. I can also take f of x and subtract it from g of x, which is the same thing as f minus g of x. I can take f of x and multiply it by g of x, which is the same thing as fg of x. And I can take f of x divided by g of x, and it's the same thing as f of g of x. Here's an important note. The domain of your new function is all those numbers that belong to both domain of f and domain of g. It's the most restricted. The zeros of the denominator are excluded from the quotient. So now what we're going to do is look at defining new functions algebraically. We have f of x, we have g of x. Find the new function and give the domain of each. So what I'm going to do here is I'm going to take the first one and I'm going to add it to the second one. Now the domain, I'm going to write up here, the domain of f is all reals. And the domain of g, in this case, is going to be where you can have -1 to infinity. Now if I add these two together, I have to go to the most restricted. So the domain of this new function is -1 to infinity. I cannot include anything that's going to make that negative. Now I'm going to subtract these. And then the domain, again, is going to be -1 to infinity. It is the most restricted. I'm going to multiply these. And again, the domain is the most restricted. I'm going to divide these. Now when I divide these, I can't have -1 because that'll make that a 0. So now I'm going to restrict it even further and say I cannot include the -1. Now if I took negative, or the GG, that just means I take the square root of x plus 1 times the square root of x plus 1, which gives me just x plus 1. And again, I'd look at this and say all reals. However, I didn't have all reals to begin with. So it's going to be the most restricted. Now you did some composition of functions before. It actually looks like this fog. And it can be written as f circle g, which is the same thing as f of g of x. And the domain of this particular function is all the x values that are in the domain of g that maps to the domain of f. So basically what I have here is I've got x values that go into the g of x, and then what comes out of the g of x goes into the f of g of x. So the domain of x, the domain of the g goes in here, and the domain of this one happens to be the range of this one. So now let's see what we've got here. We've got f of x, we have g of x. We need to find f of g of x and g of f of x and verify that they're not the same. So what I'm going to do is I'm going to first find the domain of f. I can use any real in here, so that's -infinity to +infinity. The domain of g, I can only use 0 to infinity. And now what I need to do is f of g of x, which happens to be f of g of x. And I'm going to see how that compares to g of f of x, which is g of f of x. So now I come along here. My g function happens to be the square root of x. My f function says I take e, and whatever this argument is, I put it in there. So that's what the f of g of x is. This one says I take whatever my f is and I put it in here. And then I take whatever my argument is and I put it in here. Notice, these are not the same at all. So now what do I have to do is I have to look at what's the domain of this one, the domain of f of g. Let's see what we get. I only have positives and zeros, so all I'm going to have in here is positives and zeros. In this one, I can put anything in the e to the x, but I cannot have, I could put any number. I could put a negative, and that makes that 1 over e. I can put a 0, that makes that 1. Either way, I'm never going to get this to be a negative. So the domain of g of f is going to be all reals. Now, since these two functions are not the same, therefore, f of g of x and g of f of x is not commutative. So you can't make it into the other one. They're not going to be commutative. Finding the domain of a decomposition. All right, we're going to find the domain of this composition, and here we have the domain of f. I can use everything. This one, I can only use 0 and up. So now I need to find g of f of x. That's g of f of x, which is g of x squared minus 1, which when I plug it into here, it happens to look like this. Now I got to find the domain of that one. This allows me all reals, and I put it in here, but what is it that I cannot have in here? I can't have this equal a negative number, so let's solve. X squared equals 1, x equals plus or minus 1. So what I'm going to do is I'm going to actually either do a sign chart, or you can look at the graph. That's what I've got. What's going to make this negative? Well, let's put in here a negative 2. When I square it, this will be positive. Let's put in 0. When I square it, this will be negative. When I put in 2, this will be positive. So this here is going to make this value negative. So my domain of g of f, I don't want this. I don't want negatives underneath the square root. So I want to go negative infinity to negative 1, and I can include them because I can have zeros, and from 1 to positive infinity. And that would be for g of f. Let's do the same thing for f of g. Now remember, that's f of g of x. These two domains stayed the same. I'm going to take f of, well, what's g of x? It's square root of x. Now I go to my f function. It's whatever the argument is squared minus 1. Well, let's put that in here, and we get x minus 1. Now if I look here, I got to look at my domain. Have I allowed any negatives? No. So if I take f of g of x, I'm allowed 0, and I'm allowed all the positive numbers. So I'm done with that example. Now if we look at example 4, we're trying to see if we can go back to what we originally had. Now this is a much more complicated function, and they said, well, find the function so that you have g of x equal to something that when you put into f, you end up here. So what I'm going to do is I'm going to do some guessing. I'm going to say that g of x equals x plus 1. And then I'm going to say that f of x equals whatever this argument is squared minus 3 times whatever this argument is plus 4. So we're going to write it like that for now. And I'm going to see if what I get is the original. Well, I want to take f, this is my check, f of g of x. Let's see if I end up with what h of x is. G of x happens to be x plus 1. And f of x says I'm going to take the first one, square it, minus 3 times the second one, plus 4. It checks out. So this is a good decomposition. It's not the only one, but it's the easiest one for me. All right, I'm going to guess that g of x is what's inside, and I'm going to guess that f of x is the square root of x. So now what I want to do is I want to verify that this ends up giving me what the h is. So f is x squared plus 1 And then I plug it into here. And yeah, that works. So here's what my answer is going to be. Now what happens if I want to model a function with modeling with function composition? All right, now modeling with function composition. In the medical procedure known as angioplasty, doctors insert a catheter into a heart vein through a large peripheral vein and inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. Find the volume after t seconds. So we know that the volume right now is 44 cubic millimeters per second. I want volume, which is just cubic millimeters, so I'm going to multiply this by t seconds. The units goes away and I end up with the volume being 44t millimeters cubed. You didn't get a number, but we do have an equation. When the volume is v, what is the radius r? So what that means is that we're now going to solve for r. So the volume, and it's a sphere. So volume of a sphere is 4/3 pi r cubed. We want to find r, so that means we're going to solve for r. So to solve for r, I'm going to take v equals 3/4 pi, or no, v times 3/4 pi equals r cubed, and then r is going to be the cube root of 3v/4 pi. So I take the volume, which is 4/3 pi r cubed, and I solve for r. Remember, this is 4 pi over 3, so when I want to get over to the other side, it's the reciprocal. So it's the cube root of 3v/4 pi. There's our general equation. Write an equation that gives the radius as a function of the time. What is the radius after 5 seconds? So we have volume in here, we don't have time. So I'm going to substitute what I got up here. 3 times 44t all over 4 pi, and that will give me the radius. And then we're asked to find the radius after 5 seconds. So what I'm going to do is I'm going to plug in 5 seconds for the time and see if we can solve it. So now when I put this in the calculator, I am going to get 4 goes into this 11 times, and I've got 33 times 5 cube root, and I punch it into my calculator and I get 3.74 millimeters. That is the radius after 5 seconds. Any set of ordered pairs in the form of x, y is what we call a relation. We talked about that in that handout I gave you at the beginning of 1-1. Where anything can be related to something else, it's not necessarily a function. Now, determine which of the ordered pairs are in the relation defined by this equation. So what we're going to do, if this is x, y, x, y, x, y, we're going to substitute 2 squared times -5 plus -5 squared and see if this is true. So 4 times -5 is -20 plus 25 equals 5. Now that's true. So this is in the relation. We're going to do the same thing with 1 and 3. 1 squared times 3 plus 3 squared, does that equal 5? So now I have 3 plus 9. 3 plus 9 does not equal 5, so this is not in the relation. Now let's do the same thing with 2 and 1. 2 squared times 1 plus 1 squared, does that equal 5? Well, 4 plus 1 is 5, and that one works. So this is in the relation. Now we have to find out, is the relation a function? Well, we have the same 2 going to two different y's, so the answer is no, it is not a function.